Let's play around with some transformations, and we'll use this function to do it. Okay, so we'll transform this function. Now, I don't have a mathematical formula here for it. I just have the graph. Okay, so we have the point 2, 2, the point 4, 3, and the point 6, 1. And we will use those points to study what happens when we perform various operations on this function. For example, what happens when we add 2 to the function? Now, of course, the x's don't change. So we put in a 2 for x, and we get f of 2, which is 2. But then, after we get that output, we add the 2. In fact, we do that to every single y that we get. So all these y's are increased by 2, and what that does to the graph is it raises it up 2 units. So that's what happens when we add a number to a function. If we subtracted a number, of course, it would move the function down. Now, what happens if instead of adding the number to the outside of the function, we add it to the inside? Well, now, let's think about it this way. If we want to get those y values, the same y values as we got from the original function, what do we have to do? Well, we have to choose x in such a way that we compensate for the fact that every time we put an x in here, we're adding 2. So we need to move to the left. We need to get numbers to the left. 2 numbers to the left. In other words, I need to subtract 2 from every value of x from the original. And what that does is it moves the whole function to the left. Okay, now, let's suppose we've got 2 times f of x. Okay, so up here, these are rigid shifts. Now down here, this one is not a rigid shift. It's 2 times f of x. Now, what happens here is the x's are all going to remain the same. The action is going to be on the y's. What happens is, as we plug in a value for x, the function gives its output, and then it gets multiplied by 2. In other words, all the y's are multiplied by 2. And the effect of that is it stretches the function out vertically, like this. Okay? So it's a vertical stretch. Now, let's look at another one. Let's suppose that the 2 is on the inside of the function, like this, f of 2x. Now, the y's, let's suppose we want to keep the y's the same. How do we compensate for the fact that every time we put an x in there, we're multiplying by 2? Well, from the original 2, 4, 6, those original x's, we need to divide each one of those by 2 so that when we plug them in and they're multiplied by 2, they'll give us the same output on the y. Now, what that does is it affects the x this way. Notice, here is our new function. Things happen faster, right? Now, notice in the original function, the green, we had 2, 2, we had 4, 3, and 6, 1. Notice how this thing is kind of stretched out. When we multiply by 2 in here, it compresses everything. Now notice, this thing started here at 2 and it ended at 6. This thing started at 1 and it ended at 3. So notice, this one went 1, 2, 3, 4, and this one went 1, 2. Notice there are 2 little segments here between the start and the finish of the graph horizontally. Over here for the green one, there's 1, 2, 3, 4. So it looks like what's happening is this function does what it needs to do twice as fast. Instead of starting here at 2 and ending at 6, it starts at 1 and ends at 3. So it compresses the graph. It's a compression. And we do the opposite to the x's of what it says in here. It says 2x. We compensate by dividing by 2. Now let's suppose we have negative f of x. Okay? Now the x's are all the same. However, every time we evaluate this function, we're taking the negative of it, and that has the effect of reflecting the graph into the x, right? It turns the graph over, right? It kind of flips it. 6, 1 becomes 6, negative 1. 4, 3 becomes 4, negative 3. And 2, 2 becomes 2, negative 2. So there's some examples of how we can deal with some transformations and the effect that these have on the function.